Turn on your videos. All right. So the first thing we're going to do today is look at the problems at the end of chapter 7, and then we'll go right into chapter 8.
Good morning. My computer was dead.
Your computer is dead?
No, it was dead. I just got it to turn back on.
Okay. All right. Well, I'm glad it survived. Um, so let's take a look at problems here. Hopefully you can see the ebook that I have here. So we should get to number 5. Yeah, it's number 4. I think we started this last time but didn't complete it. Is that right? Did we do this last time? Chapter 7?
Yes.
We did do all the problems in chapter 7? Did I show you all of them?
No, I don't think
No.
so.
All right, so let's go over those again. So problem number 4, exercise 4 at the end of the chapter, shows some exam results. And so these are the exam results, not in any particular order. And then I created a stem plot for these. These are all 2-digit numbers. So the tens digit was the stem part, and the ones digit is the leaves. All right. So I think I showed you how this is done last time, but I'll show it to you again. So let's get to the solution here. All right. So there were 28 test scores, and I put them in numerical order with along this column here, the 3 up to 9. These are the tens digits for all of the numbers in the data set, and then on the right side of the vertical bar here are the actual ones digits. So to read this, it would be 32, 55, 60, 61, 62, 64, 64, 68, and so forth. That was part A, and I think part B, they said, why don't you create a stem plot that had lower and upper for each of the tens digits, where the lower would go from 30, like for 3L here, would go from 30 up to 34, and 3H would go from 35 up to 39. And the advantage of doing it this way was that you could see that the 32 is much away from all of the other values in a data set. So it looks like an outlier at least. Okay. Let's go back to the book. So that's what I did for number 4. And then number 5, I wanted to create a histogram for this data. Now, I'm not going to ask you to create either a stem plot or a histogram, but you should be able to read one. You should be able to look at it and know exactly what you're looking at, and to be able to interpret it. Okay. Now the histogram, the way I did it, and I do this in my Stat 1 course, but I'll just explain in general how I did it. So I'll go back to the solutions. All right. So along the x-axis, I've created these classes. Classes meaning they're groups. I created 6 groups, and each group is 12 units apart. Right? They're from 32 to 44, from 44 to 56, and so forth. Now I created it so that every single value in the data set, and there how many are there in this data set? There are 28. Sample size 28 test scores. So we call that sample size, small n. And I classified each one of those test scores in one of these 6 intervals. So in other words, the test score 32 would show up in the first one, from 32 to 44. Test score 55 would show up in the second one from 44 to 56, right? Like that. And the height of each of these rectangles is the number of values in your data set that are in this group, right? So what's the group? Just the actual test scores. Any test scores that are from 32 to 44 are in class number 1. In class number 2, any test scores that are between 44 and 56. Same thing with any test scores between 56 and 68. There were 5 of those numbers. How do we know? Well, if we go back from 56 to 68, well, for 56 to 68, and not including the 68, there is 60, 61, 62, 64, and 64. Now we don't, the 68 does not get included in that class. Why? Because it goes from 56 up to, but not including 68. The 68 goes into the next class. Right? That's how you read it. Any numbers from 32 up to 44? Any numbers from 44 up to 56? Any numbers from 56 up to 68, like that. So you just search your data set to find those numbers and you just count them. So there are 5. You can see the height here is 5. There is 5 numbers that were between 56 and 68. There are 8 numbers between 68 and 80. Let's double check that. Between 68 and 80. So 68, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, I get 9 actually. 1, 68 and 80 gets 1, 2, 3, 4, 5, 6, 7, 8, 9. I get 9 of them. And 68 and 80, I guess I should have put 9 there. All right, so should change that. And then from 80 to 92, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of those, not including the 92. Right. So I think I had to switch it. This one here should be 9, and this one here should be 8. And then the last one, there's 5 between 92 and 104. So it's 1, 2, 3, 4. Okay, so I'll make the change and give you an updated version of this. This histogram is slightly wrong. This class here between 68 and 80 should have 9, and this one should have 8. But regardless, that's what the histogram looks like. And as you can see, it's skewed to the left, which means its tails off to the left. If we drew a curve around this here, it would certainly move towards the left. All right, so that's what we mean by skewed to the left. All right, and then I explained, I think we did this last time. I think maybe I even stopped right here. To find the median, we take the ordered data set. Now remember, as a stem plot, it's already ordered for you, right? And what do? Well, we find the middle value. That's the median. Now, if the data set is odd, if the sample size is odd, that means there are like 29 numbers in a data set or 31 numbers in a data set. And we just use this little formula here. We take the number of values in a data set, the sample size, add 1, divide by 2. Right? And that the number and the number we get is the position of the median. So we just find that position in the data set, and that's the median. If n, the sample size is even, then we use the formula again, and we should get a number that has a 0.5 at the end of it, a whole number plus 0.5. And we use the number to show the first number that we find, and then the next one is the next number we find, and we average those two. So that's what we did in this case here. There are 28 numbers in the data set. So it's 28 plus 1 is 29, divided by 2 is 14.5. So the 14th number in the data set and the 15th number in the data set are going to be averaged. So we just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the 14th number is 78. 15th number is 79. We average them 78.5. That's the median. Okay, that's what we did here. Explains exactly how you do it. Many of you already know how to find the middle value in a list of numbers. That's the median. All right. And what the median means is that 50% of the numbers are less than that and 50% of the numbers are greater than that. Well, 78.5, if you look, it said 78.5 is not even in the data set. But if we count the number of numbers less than 78.5, we get how many? 14. How many numbers are greater than 78.5? 14. All right. That's the definition of a median. Half the numbers are less than that number, half the numbers are greater than that number. The mean, we just took all these numbers, all 28 of them, added them up, divided by 28, and we got the mean of 76.0357. I think I went over it last time, that this symbol here, this squiggly looking symbol, means sum or add them up. And the X means just all the values in the data set. So when you see this symbol and X, it means add them up. Divide by N, the sample size, 28, you get 76.0357. It is typical that for a skewed left distribution, the one that looks like this, where if you drew a curve around it, it would tail off to the left. The mean is less than the median. Why is that the case? Because the low value, the 32 here, when added into all the other 27 numbers, makes the mean smaller than the median. The median is just the number in the middle. It doesn't get affected by these so-called outliers. Any numbers that are big or small don't affect the median. The median is still in the middle. So the median is not affected by outliers, but the mean is, because we're adding it into the sum when we calculate the mean, right? Remember, the mean is the sum of all the numbers in the data set in the numerator. So that includes that 32. That's going to make the mean smaller because it's this very small number. And that's why the mean is smaller than the median in a data set that is skewed to the left. Because the small values are making the mean smaller, but the median stays the same. Write that down because that will be a question on the final exam. Now, they may give you data set where it's skewed to the right. What skewed to the right looks like? It'll be the opposite of this, where most of the bars are on the left and it tails off to the right. In that case, very large numbers are making the mean bigger than the median. This is tested on in the final exam. I'm letting you know right now. And you should have a part of your notebook, if you're keeping notes, you should have a notebook where you're keeping notes. And you should have that as final exam notes, things that I'm telling you along the way. If you get it wrong because you didn't write it down, it's nobody's fault but your own. Okay, just know that. If you're not right, I'm telling you to write it down now. But if you're not doing it, you get it wrong, that's 0 points for that final exam question. Right? It could be out of 45, 50 points in the final exam, that part of the final exam, which is the core piece, that's 10 points off right there. That's like a quarter of your grade. Quarter of your grade, you got a 0, just because you didn't write it down. All right. So I'm telling you that up front, that you should write it down. Okay. Standard deviation. Now, how did you get this? There's a formula for it. And it's a complicated formula because what you're doing is once you calculate the mean, you're going to subtract the mean from all 28 numbers in the data set. So you get these, what are called deviations from the mean. And then you're going to square each one of those. Then add up all those squared deviations from the mean and divide that by the number of values in your data set minus 1, and you get what's called the variance. And then you take the square root of that and you get the standard deviation. However, in your calculator, if you got the TI-30X scientific calculator, there is a data feature in there. And as I mentioned to you last time, you should learn how to use that because it has this feature where you can open up the stat part of the data set and you can enter the data values and it will calculate both the mean and the standard deviation for you. We'll calculate both of those. So will I ask about the standard deviation? Yes, I will ask, which will force you, in a sense, to learn how to use your calculator. All right. Learn that feature. And how do you do that? Google it. All right, there's going to be YouTube videos out there that will tell you how to use this calculator and to find the standard deviation. Just Google it, do a search, and it'll teach you how to do it. All right, it's not that hard to do. Now, if for some reason your calculator doesn't do this, then I can teach you. I can have a little tutorial, maybe for a few of you who want to learn this. You can use Microsoft Excel to calculate both the mean and standard deviation also. It's very easy to do in that also. So that is something I will offer before class, test number 2 is a short tutorial how to use Excel for calculating some of these things. And then I think I mentioned last time that 32 is removed, the standard deviation would be smaller. Now, the standard deviation is also affected by outliers. Why? Because the 32 in this case, you would subtract the mean from that, and since the 32 is far away from the mean, when you subtract the mean from it and square it, it's a large number. So if you remove the 32 from the data set, which is asking it to do, the standard deviation would become smaller because that large number is being removed. Quartiles. I think I mentioned this to you last time. I guess, again, I'm reviewing it with you this time. There's 2 quartiles. There's what's called the lower quartile, which I'm going to call Q1, Q meaning quartile, and 1 meaning the lower one. And there's another one called Q3, which is the upper quartile. Now, the median, you're wondering why isn't there a Q2 in here? Well, the median is Q2. Q2 is the median. The median, it says, basically says that there's 50% of the data that's less than that, 50% is greater than that number. What is Q1? Q1 is the lower quartile, which means 25% of the data is less than that, and 75% of the data is greater than that. The upper quartile means 75% of the data is less than that, and 25% is greater than that number. How do you find Q1 and Q3? Well, if you already found what the median is, the median breaks the data set into a lower half and an upper half. The lower half, if you found the median of the lower half, that's Q1, that's the lower quartile, using the same rule as we found the median for the whole data set. So for the lower half of the data, if you found the median of that, that's Q1. We took the upper half of the data set and found the median, that's Q3. All right, using the same rules as we found the median for the whole data set. So when we do that.
Wait a minute, Q3 is what, the upper what?
Upper quartile.
I mean, I'm going to say
Quartile.
median of the high.
Think of quart of milk. Quart of milk. All right, 4 quarts make a gallon. 4. So what quartiles mean? 4. It means 25% of the data is between the lowest value in the data set and Q1. 25% of the data is between Q1 and the median. 25% of the data is between the median and Q3, and 25% of the data is between Q3 and the maximum number. And you'll see that when I graph a box plot, which is a visual way of showing that. All right. So I show you how to calculate Q1 and Q3. I've corrected those things in here. All right. And then I showed you the book comes up with what's called the 5-number summary. This box here. You need to know this for the test, next test. The top number is the median. The number on the next row of numbers here, 66 is the first lower quartile, 84.5 is the upper quartile, 32 on the next row here, 32 is the smallest number, 98 is the largest number. This is called the 5-number summary. And the 5-number summary allows you to graph what's called a box plot.
Can you say why? I'm sorry. Can you say why the 66 is the low quartile? I'm sorry, I'm writing this down because I'm having.
Well, it's all written here. Yeah, it's all written in the notes.
Yeah, I need you to say it though, Professor, please.
Oh, all right. It's you're taking the median of the lower half of the data. All right.
I'm talking about
The 14 lower numbers, you find the median of that.
Yeah.
and you're averaging those two numbers in this case. There's 14 numbers, so it's going to be the 7th and 8th numbers in the data set. 64 and 68, you're averaging it. That's where the 66 comes from. And Q3, the upper half, it's the 7th and 8th numbers in the upper half of the data set. The half of the data set that's larger than 78.5, the median, and you're averaging 84 and 85. That's where you get those two numbers. Then you can graph them using the box plot here, where the box, the left end of the box is your Q1, and the right hand of the box is Q3, and the vertical line in between is going to be your median. Now you have a number line down here, so you line up these numbers to where it should be. So 66 is around here, right? 84.5 is around here. The median is 78.5. It should be around here. The biggest number is 98. It's down this way. Smallest number is 32. Notice I have an asterisk. I think I explained this to you last time. There's an asterisk here because this is a outlier. And remember, I showed you how to calculate an outlier last time. All right, how do you do it? You calculate what's called the interquartile range. It's Q3 minus Q1. You subtract these two numbers here. 84.5 minus 66 gives you 18.5. Interquartile range. Multiply it by 1.5. You get 18.5 times 1.5 is 27.75. And again, this is a recipe. Just follow the directions. The next step is to take your Q3 number, 84.5, and add to that the 1.5 IQR, this number here. So 84.5 plus 27.75 comes out to 112.25. The rule states, and it says it in your textbook, that any numbers in your data set that are larger than this 112.25, is an outlier. Well, there are no numbers in your data set that are larger than 112.25 because your biggest number is 98. So therefore, the biggest number or no numbers in the data set are a large outlier. 98 is not an outlier. So if I was going to ask you, is the largest number in the data set an outlier, you would say no, because this 98 is not bigger than 112.25. Then you want to look at small outliers. So what do? You take this, your Q1, which is 66, and you subtract from it the 1.5 IQR, that's 27.75. You subtract it, you get 38.25. 38.25 is around here. Then the rule says, look for any numbers that are smaller than that. Well, there is. 32 is smaller than 38.25. Any numbers that are smaller than this number here is an outlier. So 32 is an outlier. We have one outlier, and the way we draw it on the box plot is we put an asterisk where there's an outlier. Now you see that this horizontal line stops right around here, and then there's this gap between there and the asterisk. Well, that's because the next largest number after 32 is 55. And we stop at 55 with this horizontal line. Okay, we stop there because the next number is 32 going to the left. 55 is not an outlier because 55 is larger than 38.25. So the only outlier here is the 32. All right, that's how you calculate it. Just have to follow these steps. It is in your textbook. But I'm showing you as an illustration in this case of how this outlier was calculated. All right. 98 is not an outlier, 32 is. 55 is not an outlier. Okay. All right, any questions about that? Again, I think you just need to follow what I did here. This is an example of what the book talks about. I think they have another example in the book. And again, this is open book, open notes. So if I ask you to a question about an outlier in a data set, you'll be able to do this with your calculator and determine whether a particular value in your data set is an outlier or not. So the interquartile range has to be calculated first. You multiply it by 1.5, and then you add that to the upper quartile to see if there's any numbers bigger than the sum of those two. If they're not, then there's no outliers on the upper end. Then you take the lower quartile and subtract this number to see if there's and then determine if there's any numbers lower than this, and there is in this case the 32. Not therefore 32 is an outlier. Again, just follow the steps like this is some sort of cooking recipe. All right, and it's literally just that. You don't have to memorize it. In a Stat 1 course, typically people have to memorize this. What I just showed you, they have to memorize it. But in your course, there's no need to memorize because you just have to know where in the textbook in chapter 7 this recipe is, and I will test it. There's guaranteed you will be tested on this, not only in test number 2, but in the final exam. So this is an important thing to learn. All right. So if the book has an example, here's another example here. Just go through it. Make sure that you can use your calculator and follow these steps, and then you should be good. Any other data set, it's the same idea. And what I will typically do for you is I will give you one of these, a stem plot. All right, I'll give you the stem plot because it's a nice way of organizing your data, right? In an ordered fashion. It's an ordered fashion. And then I'll ask you questions like the ones I've just answered from the textbook. All right, same questions: mean, median. I might even ask you for the mode, which is the most frequent number in the data set. What is the mode in this case here? Well, there is a tie for the mode because there are several numbers here that are repeated twice. For example, 64, 75, 78, 79, and 80. All of those are considered the mode because they all have a frequency of 2. Okay, if all the numbers in the data set are all different, there's no repeats, then there's no mode. But you look for the one that has the most frequent, and if there's a tie, you mention, all of them that are tied for the most frequent one. So in this case, there are several that are considered the mode. All right, any questions about that? No tricks. There's no tricks. If I give you a histogram, you should be able to tell me whether it's skewed to the left or skewed to the right. Remember, you have to know this for the final and for the test number 2. You have to know it. It's in the book. It explains it. It shows you examples. And this is an example of skewed to the left, and the book shows you examples of skewed to the right. All right. No questions about that? All right.
Ain't that school to the right? Because
Skewed.
ain't that school to the right?
No. No, again, you're doing what most students do. They look at where most of the data is. Skewed means where the tail is. If you drew a curve around it, it's tailing to the left. Where the tail is. Write it down. Just write it down. Don't try to,
What do you mean?
don't get yourself all confused about this. There's no confusion. I'm explaining what you look for. If you draw a curve around this, it's tailing to the left. You can see the tail, right?
Oh, okay. The end. Okay.
Call it tail, because that's what we say in statistics. It's the tail. It looks like a tail, doesn't it?
All right, I got
You can picture a creature that has, this is their back here, and then the tail is down here. So that's why they use the word tail, because it's like a tail.
I got you. Okay.
Yeah, and then skewed to the right would be the opposite, where
The opposite. Yeah.
where
Okay.
most of them are on the left, and then it's tailing to the right.
Right. I got it.
That would mean that the mean is bigger than the median, because there you have large numbers that are some numbers that are unusually large in a skewed to the right. All right. So I'm telling you right up front, this is what's going to be tested on. Make sure again that you write it down. And it's all in the book too. So wherever you find it in the book, tag it, say this is important. All right. And again, it's a shame that some people fail the final exam because they don't write things down. They just don't. Write, they don't read. And and then they try to guess at it when they see it as if they saw it for the first time. And as you just did a minute ago, you thought it was skewed to the right. And that would be the common answer for people who don't write things down. They'll just say it's skewed to the right and they get it wrong and they get 0 points in the final exam for this.
That's why I ask questions.
Yeah, you do. Yeah, you should. And write it down so that when you see it again, it'll be an easy question. It is an easy question if you know the answer. It's just very, very easy. Nothing to calculate. All right, that's it for chapter 7. Let's go now to the PowerPoints for chapter 8, where we're going to talk about bell-shaped curves. Now, these curves are what? These curves are, they look like that. There we go. They're shaped like a bell, right? That's why they call them bell-shaped. And what's nice about the bell-shaped curve is that we could say that the mean and the median are approximately the same. They're about the same. Which means that, and typically, where's the mean? If you draw a vertical line down the middle, where it peaks up here, if you draw a vertical line down here, it looks like the mean's around 68.2 or so. That's also the median, which means that half the data is to the left of it, half to the right of it. And you could picture it that would be true, because if you draw the vertical line here, the left-hand part of the curve and the right-hand part of the curve look the same. They're just mirror images of each other. All right, so this is some of the properties. I think, again, I went over this last time, but again, I'm reviewing because it's so important. All of this I'm showing to you, right? So the normal curve is going to look like this. Now, in a regular statistics course, you would be working with this like for the whole course using your graphing calculator. But for this course, we're just introducing this to you just so that you can distinguish between this and the other 2 types of curves that I talked about, the skewed left and skewed right. And this one, the mean is approximately equal to the median, and the mean is, and that means 50% of the data is less than the mean, 50% of the data is greater than the mean. Here is our skewed right. Remember, we just talked about that a minute ago? Money is typically a skewed right curve, money. Why? Because most people have lower incomes, and then you have these really rich people, right? Now, obviously, there's some people out there who have no income, but there are fewer people who are very wealthy, right? You've always heard this, right? 1% of the population earns like 70, 80% of the money. All right, we know that. We've heard about that, the billionaires and so forth. There's not many of them compared to everybody else. So that's what this is what it looks like, income. Or in this case, it's car insurance damage claims, but usually money-related things are skewed to the right. Unusually large numbers are down here. And this is a case where the mean, the average, is going to be bigger than the median. I think somebody asked last time when they looked at this, where's the median? Is it 6? Well, it's probably something a little bit bigger than 6. It's probably between 6 and 12 here somewhere would be the median. The mode would be at 6. That'd be the most frequent one. Then we have these unusually large ones down here. So it says here, the majority of the claims were below 5,000, right? Majority. But there were occasionally a few extremely high claims. Now these claims are in thousands of dollars, so when you see these numbers down here, you have to multiply by 1,000. So if you see 30 here, it means $30,000 claim. You see 5 or 6 down here, or 6 down here, it means a $6,000 insurance claim. Now, it says here that the total area under the curve, under what they call a frequency curve, this is called a frequency curve, the total area is 100%, right? Or 1 if we were just do it as a decimal, just 1. The total area is 100%. So if we wanted to know what percentage or proportion fell below a certain amount, let's say below 68.2. Let's say 68.25. Actually, 68.25 is the mean. We would say 50% or 0.5 as a proportion of the heights of British men are below 68.25 inches, or half is bigger than that. That would be the mean, because the mean is equal to the median. The definition of the median is half is lower, half is higher. Since the mean is equal to the median, we would, because it's bell-shaped, we would say half of the men are 68.25 inches smaller, or half of them are taller than 68.25 inches. All right. So the area to the right is 0.5, the area to the left is 0.5. If we drew a vertical line down here, we would say half of the curve is to the left, half of the curve is to the right. That's what the mean is. Any questions about that? Should be pretty, I think it's pretty intuitive, isn't it? I mean, your intuition's saying that half the curve is to the left, half the curve is to the right. So whatever the middle value is going to be your median. And in this case, the mean is equal to the median because it's bell-shaped. Normal curves are everywhere. Right? Typically, physical measurements like heights and weights are bell-shaped. Scores and tests tend to be bell-shaped, like the SATs. Percentiles and standard scores. Now, what is a percentile? Percentile, if I say the 50th percentile, that is the median. That's the median, because it's a percentile set gives you the percentage of data that's less than that value. So the 50th percentile means 50% of the values are below that number, 50% or greater. That is the median. Right? So that's what a percentile means. If I say the 10th percentile, if you scored the 10th percentile on a test, you didn't do very well, because 10%, only 10% of the people did less than you, 90% of the people did better than you. You did the 90th percentile, that's the opposite, right? 90%, you did better than 90% of the people, and 10% of the people did better than you. All right, so that's percentiles. The mean is the middle value. It's sort of the middle value because you're adding everything up and dividing by the number of numbers in the data set. That's the mean. So it's not exactly the middle value, but it's a representation of the middle value. The standard deviation is, you could say that is the average spread between data points in the data set, the average spread. Okay. And then we could also talk about standardized scores. Standardized scores. We can convert your so-called raw score into a standard score. So how does that done? Well, if you know the mean and you know the standard deviation, that is, you know the mean, which is sort of the middle value. You know the standard deviation, which is the average spread of the data. And you have a particular score for a test, for example. Let's say these are tests, let's say the SATs or something. And you want to know, what is your standardized score? So what do? You take your actual score, your raw score, you subtract the mean, and that gives you this difference between your number and the mean in the numerator, and you divide it by the standard deviation. For example, if you scored, let's say the mean of a test is 100 and the standard deviation is 16. Suppose you scored 116 on this IQ test, then your standard score is going to be 1, positive 1. How? Because 116 is the observed score. Subtract the mean, which is 100, that's 16, and divide by the standard deviation, which is 16. 16 divided by 16 is positive 1. Now, what does this positive 1 mean? What's way of interpreting it? We can say that your score of 116 is 1 standard deviation bigger than the mean. And it's true, isn't it? The standard deviation is 16 units, and the mean is 100 units. Then if you add those two, you get 116. That means you scored, when you score 116, you scored 1 standard deviation bigger than the mean. 1 standard deviation is worth 16. What if you scored 132 on your IQ test? Well, you actually scored 2 standard deviations bigger than the mean, because 2 standard deviations is 2 times 16, which is 32. 32 plus 100, 132. So 132 is 2 standard deviations above the mean. What if you scored 84 on the IQ test? Well, 84 minus 100 is negative 16 in the numerator, and you divide by 16, you get negative 1. So 84 is 1 standard deviation less than the mean. But the negative indicates that you scored below the mean, and the 1 indicates how many standard deviations you scored below the mean. So that's how you read it. Now, what if you scored 100? Well, your standard score would be 0, because if your observed score is 100, the mean is 100, 100 minus 100 is 0. 100 and 0 divided by 16 is 0. So a standard score of 0 means that you scored exactly the mean, right? That's what it means. Now, if you created a normal curve, one of these bell-shaped curves that just has these standard scores as the numbers in the bottom along the x-axis, you would have what's called a standard normal curve. Standard normal curve has a mean of 0, standard deviation of 1. Now, there's tables out there which have this standard score, and in your textbook, let me just show you, to tell you, in the textbook in chapter 8, there is a table which has these scores in it. These tables, and it's on page 175 in your, if you have the paper, 175 as one of these tables. So let's actually, let me see if go to the stop here and go to the actual textbook, the ebook. All right, let me go back to the ebook here. Go to chapter 8. All right. And let me see if I can find it in the ebook. There. Now they talk about percentiles here. Here's the standard scores here. Scroll down in this page here. Notice it mentions table 8.1. You can actually click that link, and it will give you the same thing that you see on page 175 in your textbook. There it is. This is a duplicate of what's in the textbook. All right, so that's how you find it in your ebook if you're using the ebook. Now, we're not going to be using this too much, but I wanted to show you how it works. If you had, let's just look down here. If you have a standard score of 0, let's find it. Notice that next to it, there's a 0.5. What's the 0.5 represent? The proportion below that number. Well, 0.5 is 50%, isn't it? Notice that they also have here the percentile, which is the percent below. So 50% is below 0. Well, that makes sense. But how about any other z scores or standard scores that you can come up with? For example, if I got negative 0.67 as my standard score, well, 25% of the data is less than that. My standard score is negative 0.67. My percentage below it, or my percentile, is 25%. On the other hand, if you get a standard score of, hold on 1 second, let me just move this over a little bit. All right. If we get a standard score of positive 0.67, we get a proportion of 0.75, or 75% of the data is less than that. So for z-scores, for these standard scores, negative 0.67 is your first quartile is 25% less than that, and your upper quartile is positive 0.67. Okay, so that's how you find the quartiles. But you can find any other percentile also with this table. So for example, 1.28, the percentile, this says the proportion is 0.90 and the percentile is 90%. So this is the 90th percentile. 90% of the data is less than 1.28, your standard score of 1.28. So that's how you read this table. All right. But this is more important for a regular statistics course than it is for this course. But if for some reason you're being asked a question to find a percentile, let's say if I asked you, give me the standard score for the 80th percentile, well, you look for the 0.8, the proportion or percentile, in this case 0.8 for the proportion, and then you just move your cursor over to 0.84 and you say, well, the standard score 0.8, positive 0.84 is the 80th percentile, like that. All right, so that's how you would read one of these tables. Now, let's go back to the, back to the PowerPoint. All right, continue. Okay. Now, in this particular case, you got a standard score of 1, right? If your IQ score was 116. And again, if you looked up the standard score of 1, you would find that it is the 84th percentile. 84th percentile. It means 84% of the data is less than a standard score of 1. All right, so that's not bad, right? If you took an IQ test and you got 116, that shows a pretty high IQ score, right? 84th percentile, which means 84% of the people scored less than you. 16% of the people scored better than you. Some people, of course, have low IQs because in this case, they talked about some sort of issue with, this is mom killing a baby. The mom had an IQ lower than 90, at an IQ where 98% of the population had a lower value than that. This means that the percentile, by the way, is 2%, right? If 98% of the people had a higher IQ than you, that means that 2% of the people had a lower IQ. And so that's called the second percentile. And in this case here, it asks what was the person's actual IQ, this mom here who killed the baby. And well, if you look up the standard score for the second percentile, you look it up in that table. You look up for a 2% percentile, it would be negative 2.05 is your standard score. And then you use that formula I showed you to calculate the standard score, and you just do a little bit of algebra to rearrange it, and you get a 67.2 as the IQ, or a 67 IQ. All right. Now, GREs is similar to the SATs, except this is for graduate school. So people who want to go to graduate school sometimes have to take what's called the GREs, Graduate Record Examination. And the graduate record exams that were done between these 2 years, very many years ago, almost about 30 years ago. For those scores, the mean for the verbal was 497. This is out of 800, and a standard deviation of 115. It says, suppose you scored 650 on the verbal SATs out of 800, which is a very good score. How would you get your standard score? You would subtract the mean from 650 to 497 and divide by the standard deviation 115. And you get 1.33 as your standard score. And again, if you look that up on the table, 1.33, it's about somewhere between the 90th, and 91st percentile. So it's a very high score, which means about 90% of, you did scored higher than about 90% of the people who took this GRE test. And this is a way to actually draw it over here. Notice that if you draw the normal curve, and you're assuming here a normal curve, by the way, when you use this table. All right, that's important. This table is only used for the normal curve. So here are your GRE scores. 497 is in the middle. That's your mean. It's also the median. And your 650 is way to the right here. All right. So what it's saying here is 90% of the area under this curve to the left of this vertical line, 90% of this area is the percentage of people that scored less than you, which is 90%. Right? Remember, 100% of this area is everyone. So 90% of the area under the curve is to the left of the score 650. If you converted all of these scores here to the standard scores, where the mean is 0, then 1.3 or 1.33 is what you scored here, is also 90% of that's to the left also. 90% of the scores are less than a standard score of 1.33. Okay. Any questions about that? So this is the 90th percentile. You did better than 90% of the people taking this test. And they show another example here also. Suppose this company, I guess they're in the business of removing moles from gardens, these creatures, moles. And it says the weight of moles are approximately normal, bell-shaped, with a mean of 150 grams, standard deviation 56 grams. And according to the law, wherever this place is, according to the law, only moles between 68 and 211 grams can be legally caught and removed. Any moles that are bigger than this or smaller than this apparently cannot be hunted and removed from gardens. So we have to figure out what percentage of moles can be removed. Well, for a score for 68, for a mole that weighs 68 grams, we subtract the mean and divide by the standard deviation, and we get a standard score of negative 1.46. And then for 200, any moles that weigh 211 grams, we subtract the mean and divide by the standard deviation, we get 1.09 as that standard score. So negative 1.46 is down to the left, and 1.09 is to the right. We want to know what is the percentage of moles that can be legally caught. Well, how would you do that? Well, you'd find the percentage that is less than the 68, the weight of 68. Again, using the table, you converted the 68 weight down to, you converted it to a negative 1.46 standard score. You look it up on the table. Negative 1.46 is about 7% of the weights are less than that. And then for the a score for a moles that weigh 211 grams, you converted that to 1.09 as a standard score, and if you look that one up, it's about 86% is less than that. So 86% is less than this value here. And we're interested in the percentage in between these two numbers. So 86% is the whole area to the left of the line to the right here, this whole area, including the 7%. And if we wanted to know the area in between these two, we just subtract the 7%. We subtract this area. So this whole area to the left minus this area to the left, small area to the left, gives you a percentage in between, which is 79%. This is another type of calculation that's sometimes done in when we have a bell-shaped curve. We can figure out things like this. Now, if this seems very complicated to you, it's just, again, this is more important for a regular statistics course, but if I gave you a curve that looked like this and told you, and you know, I didn't have the 79% here, but I had something like 7% over here and 14% over here, and ask you what percentage of the mole population can be legally caught according to this, you'd say 79%. How would you know that? Because 7% to the left and 14% to the right adds up to 21%. And we know 100% is underneath the curve. So 100 minus 21 is 79. Okay? All right. Now, the normal curve also has special rules, which are called the empirical rule. And the empirical rule says the following. We draw a normal curve and we bracket off one standard deviation to the left and one standard deviation to the right. In other words, let's go back to the normal curve here. Let's look at this one down here. If I have to the left here -1, which is -1 standard deviation to the left, and if I have another one to the right here, another vertical line, which is +1, the area in between -1 and +1 is 68% of the values in the data set. If we have a bell-shaped curve, normal curve, approximately 68% of the values are between -1 and +1 standard scores. That's what it means here. If we go out to 2 standard scores, that means from -2 standard score to a +2 standard score, 95% of the values fall in between those two values. And then if we go out to 3 standard deviations away from the mean, that means -3 standard score up to a +3 standard score. Almost the entire curve is taken care of there. 99.7% of the values are within ±3 standard deviations from the mean. This is another way of drawing it. So let's look at this example here. Suppose the mean of heights, adult women heights, is 65 inches. Standard deviation is 2.5 inches. And we say heights are approximately bell-shaped, right? So the question is, what percentage is between 62.5 and 67.5 inches? Well, if we add 1 standard deviation to the mean, that's 65 plus 2.5, we get 67.5 right here. If we subtract 1 standard deviation from the mean, it would be 65 minus 2.5, or 62.5. That would be over here. We would say this area here under the curve between 62.5 and 67.5 is 68% of the data. Okay, 68% of that area is 68% of the data. So we would say 68% of the heights of adult women are between 62.5 inches, 67.5 inches. Now, if we added 2 standard deviations to the mean, what's 2 standard deviations? Well, 1 standard deviation is 2.5. 2 standard deviations is 2 times 2.5, which is 5. If we add 5 inches to 65 inches, we get 70. If we subtract 5 inches from 65, we get 60. And that's plus or minus 2 standard deviations. So 95% of the data is between 60 and 70 inches. If we wanted to go out to 3 standard deviations, we would multiply our standard deviation amount, 2.5, by 3, which would be 7.5. We add 7.5 to 65, we would get 72.5. We subtract 7.5 from 65, we would get 57.5. And we would say 99.7% of the data is between 57.5 and 72.5 inches. Or 99.7% of adult women have heights between those two heights. Okay, so that's basically how it works. Now, if we wanted to know something like what percentage of women have heights bigger than 70 inches? If I ask you a question like that. Well, 70 inches is 2 standard deviations bigger than the mean, right? Standard deviation is 2.5. 2 times 2.5 is 5. 5 plus 65 is 70. So 2 standard deviations is 70. Now I want to know what percentage of women have heights bigger than 70. How would I figure that out? Well, one thing that we know is that between 60 and 70 is 95%. Okay. What's left? Well, 100 minus 95 is 5%. What's left, if we just look at these areas between 60 and 70, this area between 60 and 70, what's left, we have the area to the right here, which is bigger than 70, and we have the area to the left, which is smaller than 60. These two tails. But they are the same area because this is a symmetric curve. That means these two areas are the same. So if we have 5% left, half of it is to the left, that's less than 60, and half of it's to the right, which is greater than 70. So the answer is 5% divided by 2 is 2.5% of the heights would be greater than 7. All right, did you understand that reasoning I just said? 100% under the curve, 100% of the heights. I wanted to know what percentage is bigger than 70. Well, between 60 and 70 is 95%. 100 minus 95 is 5%. Half of that 5% goes to the left tail below 60. Half of it goes to the right tail above 70. A half of 5% is 2.5%. So the percentage of women, adult women who have heights greater than 70% is about 2.5%. And the same is true for women who have heights less than 60. 2.5%. And these are formulas that are used. Now, remember the formula for finding the standard score. Sometimes it's called a z-score. All right, z. So if you see z, it means standard score. So your observed score, or a raw score, another way of saying it, raw score, you subtract the mean. Now, this symbol here is a Greek symbol for the mean. We subtract the mean and divide by the standard deviation. This is the Greek symbol for standard deviation. Okay. So if we subtract the mean and divide by the standard deviation, we got our standard score, this is z. If we were given a z-score and we know the mean and standard deviation, then we can just rearrange this formula, and we use this formula right here. All right, this is just algebra. We just multiply both sides by the standard deviation and add the mean, and we get this formula. So if we know the standard score and we are given the mean and standard deviation, we can calculate their raw score. Okay, so this is another way of using that formula. And again, this is the empirical rule. This is the rule we just talked about with the 68%, the 95%, and the 99.7%. You don't need to memorize this, but this would be a good thing to have in front of you when you're taking a test, in case I ask you a question about this. Okay. All right. Any questions about Chapter 8? Now, Chapter 8, again, is the basis for a regular statistics course, but it's being introduced here just as an introduction so that you are somewhat familiar with it. But when we actually do some advanced statistics later in the course, we'll be using something a little bit different than this. We won't be using these formulas to come up with interpretations, as opposed to a regular stat course. We're going to be using something else, which is a little easier to use than this. But you should be somewhat familiar with what's on this sheet right here. Now, again, this notation here is a little complicated. Again, this symbol here means standard deviation. If you square the standard deviation, you get what's called the the variance, all right? And sometimes people use this notation for the normal, the bell-shaped curve. They split the n for normal, and they say it has a mean, and then they'll put a number in there for the mean, and then put a comma, and then they put a number in for the variance. And you just take the square root of the variance to get the standard deviation. This thing here. All right, so that is it. Any questions? And there is a problem, some problems at the end of chapter 8, which I will do on Thursday at the beginning of the session on Thursday, and then we're going to move into chapter 9, where we're going to look at some graphs, different types of graphs that are used. Look at some graphs, pictures, and things like that in chapter 9. All right, but we will do some example questions for chapter 8 next time. I will post that for you. All right, so that's it. Any questions? No questions? All right, so I'll stop the recording and I will see you guys on Thursday. All right, take care.